Hello dear students, in this lecture we will talk about emission spectroscopy and emission quantum yield phi-EM. As you know, the spectrum generated by the emission of radiation from sample during de-excitation, we call that emission spectroscopy. This is shown from the diagram that the molecule in the excited state reaches the ground state by the emission of photon. Now, the term de-excitation is important, meaning that molecule is already excited, which suggests that before emission there is absorption of radiation. More the molecules from the ground state reaches to excited state by the absorption of radiation, more will be the emission of radiation. So we can say that the emission intensity depends on the intensity of radiation absorbed. Now, to quantify that emission, we have a term called emission quantum yield phi-EM, which is defined as phi-EM is equal to IEM by IABS, where IEM and IABS are the intensities of emitted and absorbed light. Now, let's consider a non-reflecting sample such that some part of the incident intensity of radiation gets absorbed and some part is transmitted. Therefore, we can write I0 is equal to IABS plus IT, where I0 is the incident intensity of light and IT is the intensity of light absorbed. Rearranging the expression, we get IT will be equal to I0 minus IABS. Since we know absorbance is equal to log of I0 by IT, which is equal to log of I0 divided by, put the value of IT here, you will get I0 minus IABS. Rearranging the equation further, we get I0 by I0 minus IABS will be equal to 10 to power A. Take the reciprocal, I0 minus IABS divided by I0 will be equal to 10 to power minus A. Dividing I0 will get I minus IABS by I0 is equal to 10 to power minus A. Therefore, IABS by I0 is equal to 1 minus 10 to power minus A. So, IABS will be equal to I0 into 1 minus 10 to power minus A. This is the expression for the intensity of light absorbed. Now, as you know, phi-EM is equal to IEM by IABS. Put the value of IABS here. Phi-EM, that is the emission quantum yield, will be equal to IEM divided by I0 into 1 minus 10 to power minus A. This is the required expression for finding the emission quantum yield, that is phi-EM. Now, to find the phi-EM, IEM, that is the intensity of emitted photons, has to be calculated, but only a small fraction of emitted light is collected and detected. This small fraction of light depends on several factors, which include angular distribution, that is the solid angle of emitted photons, refractive index of solvent, wavelength, scattering of properties of sample, and sample geometry. All these factors influence IEM. So, the fraction of light is impossible to accurately quantify IEM, which prevents direct measurement of emission quantum yield, that is phi-EM. Now, for finding phi-EM experimentally, we use a reference whose quantum yield is known, and let that be phi-EM-R, and let the emission intensity be phi-EM-R, where R stands for reference. Moreover, let phi-EMS and IEMS be the emission quantum yield and intensity for sample. Therefore, we can write the emission quantum yield of reference will be equal to IEM-R by I0 into 1 minus 10 to power minus AR. AR is the absorbance of reference. Similarly, phi-EMS will be equal to IEMS divided by I0 into 1 minus 10 to power minus AS. Dividing these two expressions, we get phi-EMS by phi-EMR will be equal to IEMS into 1 minus 10 to power minus AR divided by IEMR into 1 minus 10 to power minus AS. This is the expression which is used to calculate easily phi-EMS by obtaining emission intensities of sample and reference. Since AR and AS are the absorbances of reference and sample respectively, this clearly shows that prior to emission spectroscopy, absorption spectroscopy is to be carried out. Point to be noted over here is that the conditions for measuring the absorption spectroscopy and the emission spectroscopy of reference and sample must be same. This was all about emission spectroscopy and how to find emission quantum yield. I hope you understand it. If you like my videos, do not forget to subscribe my channel. Thanks for watching. DHC.